Next speaker, sorry. So next speaker is Koji Hashimoto from Kyoto University, and he'll give us a talk about machine learning the work in APCTP. Would you please start?
Yes, thank you. I'm Koji Hashimoto from Kyoto. Do you hear me?
Yes.
Thank you. So my talk is about bulk reconstruction in APCTP correspondence. So after a very nice talk by Edward on algebraic consideration of entropy in the presence of black hole, I focus on some more kind of numerical work on how to spot the bulk gravity out of CFT correlators and other physical informations at the boundary. So this is how to make the machine learning to help us finding the bulk metric from CFT data. So this talk is based on many papers which I wrote with my collaborators, including Ohashi-san, Sumimoto-san, Izuyo, and Akutagawa-san, Sumimoto-san, and Sugishita-san, Tanaka-san, Tomiya-san. So it started actually already 4 years ago, and this whole project of using machine learning to spot the gravitational theory out of QFT data has now kind of almost complete. And I'd like to report to you how it was made and how we can make it with machine learning and what kind of physics I can extract from this machine learning technique. So before I start my talk, let me advertise a Japanese situation on funding of machine learning and physics. And in fact, there is a nice news which the Japanese government actually funded us with $10 million for 5 years to support machine learning physics research in Japan. So I think all of you can join us if you're interested in machine learning. We will host, for example, some international conferences in Japan. So if you're interested, please come to Japan after the pandemic, hopefully. So my talk is divided into 4 parts. So first, let me explain why we need, why we can such a bulk reconstruction by using deep learning. And second, I'd like to make a brief review about the methods of bulk reconstruction in the ADS-CFT, known ever. So there are several ways to actually concretely construct the bulk metric out of boundary QFT data. So I'd like to summarize some of them. And then in section 3, I'd like to tell you how the machine learning can actually spot the bulk emergent metric out of QFT data. So I use several hadronic data, one from lattice QCD, the other from hadron experiment, to actually find the bulk metric, which is supposed to be dual to QCD. And then in section 4, using the bulk metric, which was found in section 3, I construct the gravity action, which is supposed to be solved with the metric which was found in section 3. So this is the construction of my talk. So let me explain why I need this kind of technique, machine learning, to understand the ADS-CFT correspondence. So this is a standard view of ADS-CFT correspondence. Unfortunately, for generic gravitational spacetime and generic QFT, we have no proof. So there is no concrete derivation of ADS-CFT. But what we know is that there are many kind of infinitely many pairs of gravity theory in D+1 dimensions and QFT in D dimensions. And you need to take a special limit like a strong coupling limit or large N limit for quantum field theory to make the gravity side classical. And using this correspondence, For example, if you want to have a effective theory of QCD, which is strongly coupled, you take large N of QCD, and then you want to find a gravity theory which describes low energy sector of QCD. The conventional modeling of this kind of strongly coupled QFT in terms of classical gravity is as follows. So you start with quantum field theory, and then you have many data, like experimental data, lattice data. On the other hand, you have a gravity model in which you come up with a nice action. And from the action, you solve the equation of motion of this action, like Einstein-Hilbert or Diraton system. Then you get metric G mu nu. And once you get the metric G mu nu, then you solve the fluctuation around this metric. And then you have the prediction by using ADS-CFT dictionary. And then you compare this prediction with experimental or lattice data. And then you say that this prediction goes well or goes not well. And depending on that, you discard this gravitational model or you accept this gravitational model. So this is a kind of by chance. So you need to come up with a very nice gravity model to match that with the QFT data. Unfortunately, this is kind of inefficient. So what you better do is to do the bulk reconstruction. Although you start from the same, like quantum field theory, so you may have in your mind QCD, you compute experimental or lattice data from that. And from one data, you spot the metric, which actually reproduces this experimental or lattice data by ADS-CFT dictionary. This is a kind of inverse problem. So normally you start with the metric and then solve the fluctuation around the metric, and then you compare that with the QCD data. So here you go backwards. You are provided with experimental or lattice data, and then you find a metric which can reproduce this data. Once you have the metric, then you can come up with a gravitational action which solves, whose solution is this metric. So this is again a kind of inverse problem. So there is a double layer of inverse problems. However, if you complete this procedure, then you have the gravitational action. So from that, you can do everything. For example, you can compute entropy of black hole, which is one of the predictions from the gravity model, or you can solve another fluctuation around the metric, and you have the prediction. And then you compare that with other data or experimental or lattice data, and you can say whether this model is good or not. So in this way, the bulk reconstruction actually gives you a better model, which at least completely matches with the experimental data from strongly coupled QFT. So this bulk reconstruction technique, if it is successful, it is very fascinating. So the point is whether actually you can make this red arrow from bottom to top is possible or not. In particular, this part, you go from lower dimension to higher dimensions. And that sounds quite difficult. So in section 2, I'd like to make a review of the techniques which has been developed by many people on how to get the bulk metric out of data. And my way is to use deep learning. So the motivation for using deep learning is as follows. So here is a typical picture of the correspondence between the bulk spacetime and machine learning. On your left-hand side, you have a Penrose diagram of say ADS-shade black hole. And on your right, you have a neural network. And they look quite similar to each other. The difference would be that on the right-hand side, this is a kind of discretized network, while on your left-hand side, this is continuous space-time. One more difference is that on your right-hand side, you have all connected bonds between circles, but on your left-hand side, you have the definite notion of locality and causality. So there are many differences in between these two, but in one sense, these are quite similar to each other. So in what sense? On your left-hand side, this picture is actually a solution of Einstein equation, right? On your right-hand side, this deep autoencoder, for example, has a kind of optimized weights from the data, which is given at the boundary. So in this sense, so these two pictures are kind of the result of optimization of the certain equation. So from this kind of view, you can actually say that left-hand side and right-hand side are similar to each other. And in fact, you can construct a special neural network which can solve our purpose. So let me give you more senses about this, the use of similarity in our case by one slide. So here is a cartoon picture of holography. On your top side, there is a description of, say, quantum gravity in higher dimensions, where general space-time is described as this square. And on the other side, on the other hand, you have quantum mechanics in lower dimensions. For example, the alignment of spins here. This is a quantum system. And you want to make a bridge between these two. So what kind of quantum mechanical system given gives you a classical gravity space-time? So this equality, founded by Toft and Susskind and Maldacena, actually has been developed to many situations, including condensed matter physics and neural network. So for example, if you want to solve quantum mechanics in conformal fixed point, then there is a very nice use of tensor network. Tensor network is the most efficient way to reproduce the critical phenomena in quantum mechanics. And in fact, Swingle in 2010 interpreted this tensor network as a kind of discretized ADS space-time. So if you go deep inside the tensor network, you have a reduced number of tensors that reproduces the conformal scaling of ADS space-time. Now, back in history, in 2017, in fact, there is a newly discovered network which go better than tensor network. So what is that? That is the neural network. So Kari and Troyer in 2017 considered a deep neural network to represent a quantum wave function and then make an optimization for a given Hamiltonian. And they found that this neural network can do a better job compared to the other hypotheses or assumptions or answers which human beings have thought about. So the question is that since we now have a very good manufactory of neural network to represent quantum mechanics wave functions, how can we actually go to the top picture, the general space-time? Since Swingle, in fact, interpreted this tensor network as a complete homogeneous anti-digital space-time, so now we are motivated to regard a certain kind of neural network to be a general space-time. Since, as I said, neural network is automatically optimized to formulate your system, it is like it automatically finds your gravity space-time by putting the boundary data, which is actually sitting here, right? So this is very similar to our problem of bulk reconstruction. Now we have only the data here. For example, the hadronic data of QCD is put here, and the neural network is optimized. And for the special case of interpretable neural network, you can regard this inside of deep neural network layers to be a kind of space-time. So in this way, we can solve the inverse problem. So this is my motivation. So after this section 1, I'd like to go to section 2, a review of bulk reconstruction. Now, so here is a very brief, a kind of private privately seen summary of bulk reconstruction methods. Of course, there are many other methods, but if your purpose or aim is to find a concrete metric function out of QFT given data, then there are not so many methods. There are methods for example, operator reconstruction, or kind of entanglement reconstruction, but most of those are actually working for background ADS spacetime and only the fluctuation around it. So here, I'd like to concentrate on more general methods which can actually find a bulk metric other than just homogeneous pure ADS metric. So reconstruction methods are listed here. For example, holographic renormalization. From a given expectation value of energy momentum tensor in QFT, in fact, you can construct the bulk metric out of the energy momentum tensor. But here you assume the use of Einstein equation. So only the solution of Einstein equation comes here. If you use other methods, for example, entanglement entropy reconstruction or quantum computational complexity reconstruction, then from those, in fact, without use of Einstein equation, you can find the bulk metric. You can also use quantum correlators of QFT at strong coupling, with which you can actually do the bulk reconstruction to find the metric. And also, very similar to this entanglement approach, you can use Wilson loop expectation value to reconstruct the bulk metric. And I'd like to make a brief review about this Wilson loop method since I developed it. And also, in this talk, I'd like to use this ADS deep learning technique, which I'd like to review in section 3. So let's focus on Wilson loop or entanglement or complexity reconstruction as a review. First, please note that, in fact, ADS-CFT correspondence is made out of many kinds of surfaces. So if you, for example, consider 1+1 dimensional surface, then this is a so-called wall sheet, and then it corresponds to Wilson loop. If you start with, for example, D-1 dimensional plus no temporal direction surface, then this is called Ryutakanagi surface. It corresponds to entanglement. If this is D+0 dimensions, then this is called the volume, and it corresponds to complexity, blah, blah, blah. So since gravity system doesn't have a local kind of observable, you need to introduce some surfaces or higher dimensional objects which are stuck to the boundary of this space-time so that it has a physical observable. Then you have a corresponding physical notion in quantum field theory. So I would say that the ADS-CFT is made by surfaces in this way. So let me concentrate on this Wilson loop case. The Wilson loop in gauge theories are given by this well-known formula. The W is expectation value. W expectation value corresponds to the core potential, for example. And for this case, W needs to be taken to be the exponential of this Wilson loop, where a gauge field is integrated over this rectangular shaped path. And now in ADS-CFT correspondence, by the famous work by Modasina and Lee and Yi in 1998. In fact, if you start with, for example, generic asymptotically ADS spacetime, then putting a Nam-Goto string, and then assume that the end of the Nam-Goto string is on this rectangular shaped Wilson loop, then computing the area of this Nam-Goto wall sheet, you get the core potential. So this is the dictionary in ADS-CFT correspondence about the Wilson loop. So what you do is for a given metric, you compute the configuration of Nam-Goto string, and then you get the Wilson loop. the bulk reconstruction means that whether you can go backwards like this. So for a given quark potential, E of R, where R is the separation between quarks, can you get this metric? The metric is given by, for example, here, the unknown function f of eta. You just assume that it's asymptotically ADS, but this functional form is unknown, okay? Then whether you can find this f of eta function out of this quark potential, that's the question. And in fact, there is a formula. We can find a formula to reconstruct the bulk metric. I don't go into the detail, but here is a formula. So for a given E of R, you can actually find this f of beta. So you need to solve first some differential equation and also integral equation, but there is a concrete formula to get back to the bulk metric. So in this way, for a given kind of surface technology, you can actually get the bulk metric out of this data. And so going back to this list here, for example, you can start with entanglement, and then you can get bulk metric. Or you can start with Wilson loop. For the case of gauge theories, you can get bulk metric. Or you can use, for example, correlators, including the so-called method of light cone cuts, then you can get the bulk metric. So in this way, there are several ways to go backwards. But some of them have good ways, good points. Some of them have bad points. For example, for the case of this Wilson loop, since the input function is only the quark anti-quark potential, so you can fix only one function in the metric. So in the case of zero temperature, you have only one function here, which needs to be determined. But if you go to finite temperature, there are two independent functions unknown. So in that case, you need more data. Just quark potential is not sufficient. For example, you need, in addition to the temporal Wilson loop, you need spatial Wilson loop to actually find two independent functions in the metric. So as you can see, this technology actually depends on how many data you have, and also what kind of generic situation in gravity you want to consider. Going back to the list. So here among these things, the deep learning technology, which was only used so far for very symmetric spacetimes, can be actually enhanced and generalized to generic spacetimes. So there is a hope that this ADS deep learning correspondence can work for more general spacetimes. So after that being said, let me go on to section 3, where in fact I can use deep learning techniques to find the bulk metric. So the situation is quite simple. So I just use the most popular kind of ADS CFT dictionary, in which I consider a classical scalar field in the background of unknown 5-dimensional curved space-time. So this is the scalar theory, where phi is the scalar in the bulk, and then you have some potential term. So this scalar theory is in 5 dimensions, and you have at finite temperature, you have two unknown metric functions. One is in the temporal component, the other is spatial component. And I put this component to be 1 by choosing a gauge. Also, this potential function V of phi, this is also unknown. So for example, in phi-4 theory, you have two parameters. One is this L, the other is this lambda. So L could be ADS radius if you fix this mass term. But this 3 can be also arbitrary, but in this work, I just fix it to just 3. Okay, so the setup is quite simple. This is a bulk theory of scalar field. And unknown background metric. So here in this picture, I draw the bulk theory, phi of eta, where eta is the radial coordinate of this ADS-like direction. On the one hand, you have a black hole horizon. On the other hand, you have ADS boundary. The metric here is unknown. So what you do is to solve the equation of motion of this scalar field theory in this bulk in the normal ADS CFT correspondence. So if you know this background space-time, then it's easy. You just solve the equation of motion. Then solving the equation. So after solving the equation of motion, what you get the concrete profile of this scalar field phi. So phi asymptote to some configuration at the asymptotic ADS. And from that, you can actually extract the CFT data. For example, the data comes from phi 0, which is the boundary value of this phi, and also the partition function of this scalar field in the bulk. And this is the data of CFT. So the question is, for given data, can you actually find backwards these red shaded parameters? So let me summarize the dictionary of ADS CFT for this simple model. So first, what is the constraint about the boundary condition of the metric components? I have two unknown functions, f and g, but f and g, they go to pure ADS when eta goes to infinity. This is the asymptotic ADS condition. The other condition is that at eta is 0, it goes to black hole horizon. At the black hole horizon, this function f goes like eta squared, and the function g goes to non-zero positive constant. So this is the standard black hole horizon condition. So these two conditions need to be satisfied for the bulk reconstruction. And also the dictionary between ADS CFT, the ADS side and CFT side is as follows. So as I said, at the ADS boundary, you solve the equation of motion of scalar field phi and expand it around eta infinity. Since it is pure ADS space-time at the boundary, near the boundary, so you can actually find two modes, which is one is non-normalizable mode, the other is normalizable mode. The coefficient of non-normalizable mode is, for example, quark mass, and the coefficient of normalizable mode is chiral condensate. So in this way, so if you specify the corresponding operator with the corresponding QCD operator, for example, in this case, chiral condensate, then you have the mapping between the scalar field and the QCD quantities. So in this case, quark mass and chiral condensate. On the other hand, at the black hole horizon, you need to impose ingoing boundary condition. And ingoing boundary condition for a time-independent situation correspond to just Neumann boundary condition at the black hole horizon. So these two are the boundary condition for the scalar field, which is a solution of this equation motion for the scalar field. So I think the issue is clear to you. So in our case, we need to do a bulk reconstruction. So what we need to do is, for a given relation between quark mass and chiral condensate, and that is given by lattice QCD, for example, then can we actually find f and g, the metric functions, which satisfy these conditions? So for that purpose, quark mass and chiral condensate satisfy a certain relation by lattice QCD. And using that condition, we need to solve backwards in this way, from bottom to top. So how can we do that? So as I said, if we regard neural network as a bulk space-time, then we can do the bulk reconstruction. But for that purpose, we need to make sure that neural network actually mimics the scalar field equation exactly. So let me find a mapping between neural network and the scalar field equation of motion. So this is a mapping from equation of motion of scalar field to the neural network. So neural network is simply a kind of propagation of data at the boundary to deep into the bulk. Here, we have the equation motion derived from the action which I mentioned earlier. The equation motion consists of, so I assume that it is time independent. The phi is time independent and also spatially independent, except for the eta direction, which is ADS radial direction. So this is the equation motion. Here, h of eta, this is an unknown part since it is coming from the metric function f and g. Only this combination of f and g comes into the scalar equation motion in this way. And also note that this potential v is also unknown. So these two unknown functions can be determined by neural network in the following way. So first, I consider a mapping of this equation motion to the neural network propagation. The neural network propagation means that once a value of phi is given here, and also its derivative is given here, then it propagates toward the deeper into the bulk and reaches the black hole horizon like this. So this simple discretization of equation of motion of this thing can have a neural network interpretation as follows. So first, you discretize the eta direction by lattice spacing delta eta. Then this equation of motion, by introducing the conjugate momentum pi, which is conjugate to phi, this equation motion is mapped to this kind of Hamilton equation of motion, where phi and pi at the place eta is mapped to phi of pi at eta plus delta eta by this equation. Okay. The unknown part h of eta appears here. And also the potential term, which is also unknown, that appears here. So in the equation of motion, or Hamilton equation of motion, there is unknown part here. If you represent this phi pi goes to phi pi mapping as a neural network in this way, then these green pipes, so these things are kind of unknown since this maps pi to pi, and from pi to pi mapping, you have this unknown part, right? So this unknown part is mapped to these green things. On the other hand, these black solid lines, they are actually already known. For example, from phi to phi, this is just a multiplication of 1. So this phi goes directly to this phi, blah, blah, blah. So in this way, including this unknown part, you can interpret this equation of motion as a neural network. Neural network means that once you are given a consistent set of input and output, then the internal network function is optimized. So in our case, phi and pi, these relations, this relation between phi and pi is given by lattice data. And also the result, the output here, is given by black hole ingoing boundary condition. So at the boundary here and here, the conditions are fixed. A neural network is optimized to find a concrete explicit form of these green pipes, which gives you the metric function. So let me go a little bit more detail. So the data which I use is the chiral condensate as a function of quark mass. So horizontal line is the quark mass. The vertical line is for chiral condensate. And then these blue dots, those are the data of lattice QCD. And orange dots are kind of false data, which is necessary to train the neural network. Okay. So this is the functional relation between quark mass and chiral condensate. And I use this as the initial condition of the neural network, which I've shown before here, and then demand that conjugate of phi is equal to 0 at the black hole horizon. Then I optimize the neural network. Then I find these functions, the green ones. The network optimization is quite straightforward numerically. And starting with a zigzag value of a metric function, in fact, you can optimize the neural network in seconds. So here is a result. So finally, this neural network finds a nice configuration of metric function. And with this use of metric function, the data is optimized as this green crosses. So in addition to this machine found metric function, also the parameters in the potential of the scalar field, like ADS radius and the coupling constant, phi 4 coupling constant, they can be determined by neural network. So in this way, the bulk scalar field configuration and also the bulk scalar field action parameter, ADS radius and coupling constant, and the bulk metric function, all of them are determined by the neural network. So in summary, what I said is that for a given QCD data, like this chiral condensate, you can actually find the neural network, which is the result of the weights optimized by regarding neural network as the bulk spacetime. Do you have any questions so far? If not, I proceed to another formulation of finding bulk spacetime out of, say, hadron spectrum. So in the previous example, I used chiral condensate versus quark mass data. But here, instead of that, let me use hadron spectrum. For example, low meson spectrum. Low meson spectrum was well measured in experiments, so we know a lot about that. So let's use that to find the bulk metric. So what is the ADS CFT correspondence? As is very well known, this is the bottom-up ADS QCD model for meson spectrum based on Katz, Son, and Stefanov in 2006. So it is based on not the scalar field, but a vector field in 5-dimensional dilaton gravity background at 0 temperature. So here, I do not go into the details of this formulation, but the point is that in this work by Katz, Son, and Stefanov, for fixed background metric function, you can solve this vector field equation motion as a kind of fluctuation. And then from that, you pick up normalizable modes and then find the time oscillation of this normalizable mode, which is actually a dictionary to get the hadron spectrum. Okay, so what you need to do is for a given metric function, you solve the fluctuation equation of motion, and then you get, again, spectrum. And I need to go backwards. So for a given spectrum, how can I find the background metric? The idea is almost the same as before. So since for this procedure, you need to solve the equation of motion of this vector field in the bulk, you reinterpret this vector field equation of motion as a neural network. And in the neural network, the unknown bulk metric appears as a weight. So for this purpose, I need to generalize slightly this equation of motion, which was used for the scalar case, to include the hadron spectrum part, omega squared. So this is a neural network representation of the bulk equation of motion of vector field. what you do is to discretize this eta direction or z direction in this case, and then find out what is unknown part, and then embed it into the neural network weights. So green lines correspond to the unknown metric function, and black solid line correspond to a fixed weight. So for the data, I use particle data group data for row meson masses. For example, the lowest row meson resonance is this, and the second resonance is this. So if we plot this in a one line, then around here you have a row meson, and around here you have excited row meson. So blue dots are positive data. On the other hand, you have orange points which are necessary for training of neural network, and those are negative data. And using this data, I can run the neural network, and then a neural network automatically finds the optimized metric, which looks like this. So I'm going to use this in next section, but so if I summarize this section, so you can see, I can say in this way. So for given hadronic data, for example, this case is row meson mass data. The previous case is chiral condensate data. So you put it in the neural network, and then bulk metric can be found by optimization of neural network if we regard neural network as a space-time. So this ends the section 3, and then I go to section 4, where I use the gravity metric to reconstruct the gravity action itself.
Koji, I have one question.
Yeah, please go ahead.
Yeah, about the ADCQCD model.
Mm-hmm.
Okay, could you show me the slide? Just one page before this. Oh, yeah, here.
This one?
Yeah, so I was just a little bit confused about the input data and omega, the training data.
Mm-hmm. Mm-hmm.
Right. So in your schematic structure of the neural network, it seems that omega was the training data. But you said again that was the input data. I was a little bit confused about that.
So I think the usage of the word input data and the training data is almost the same for me. Does it resolve the question? Here, omega is input here, and this is training data. And also pi and its conjugate. So this is a vector field, and its conjugate is pi.
Right.
So these are supposed to be a normalizable modes in the bulk, so it goes to 0 at the boundary.
Right.
So 0, 0, and positive data, that is input parameter.
Mm-hmm.
And training data consists of the input and also output.
Mm-hmm.
And here output is just V is equal to 0 since you have normalizable mode.
Mm-hmm. Mm-hmm.
So all of this work as training data, and you start to.
Okay. And you used only the first two lightest modes for this?
Yeah, that's right. So I used only the first two lightest mode. And for example, the width of these are from PDG data, for example, you can take.
Which I see. Now I was confused about just the initial data and training data, but I understand now. Okay, thank you.
Thank you very much. Thank you. So if I make a comment on that, of course, if you have more data, then the bulk metric becomes more precise. So I took only the ground state row meson and the first excited row meson. But if you look at the PDG data, then you have second excited, third excited, and blah, blah, blah. The width goes wider and wider, but you have the data. So of course you can use it. But problem is that if you include more higher mesons, then the training becomes quite difficult. Maybe it is because the limitation of this model to reproduce all the information would be more difficult. So here we took only two excitations. but maybe you can actually make this model more precise by including more excitations.
So I have a question.
Yeah, please go ahead.
In this case, so you have QCD data and you expect that some action can explain the data. So, I mean, assume some model, and so we can have answers even though we know some function of in the metric. So we want to have that functions by using machine learning. But I have a question. So if we have some QCD data, can you know about, I mean, the model information of the model, also what we should have? I mean,
that's a good question. Yeah, I will explain that in section 4, in fact. So I generalize the space of the model, and then yeah. So you are right here. For example, for the model of hadron spectrum, you need to start with this vector field model, right?
Yeah.
But of course, you can add more terms here, and you can modify or generalize this model.
Yeah.
But if you have a neural network representation of the equation of motion of this generalized model, then you can always optimize the parameters.
Okay,
right?
I see.
So this is the simplest case. So for example, if you add, say, more difficult, complicated coupling between metric and dilaton and this vector field, you can do that. And then you discretize this equation of motion, then you have a little bit more complicated neural network.
Yes.
And you can optimize it. Yeah.
Okay, I see.
Yeah, so I think that's a very good question. So since usually in bottom-up approach of holographic QCD, you need to specify your model. But here, once you can have a map to neural network, then you can generalize the model in this way.
Yeah. And I have one more question.
Please.
And this machine learning process is, I think it comes from some concept of holography. So, but in holography, so if you have an action and we calculate then get results from near some quantum criticality like that. So I mean, so in that case, QCD data, if we have some QCD data at high temperature like this, I mean, can you explain? So I mean, can you have the model like this in that case, even in that case?
Yeah. So if the temperature is so not very large, but close to the crossover phase transition temperature, then it is known that the QCD coupling constant is still large. For example, by RIC experiments.
Yes.
So we believe that this holographic modeling is possible for that region. But if you go too much higher temperature, then the coupling constant decreases and holographic description actually breaks down.
Okay. See, so you found that data can explain this holographic picture, right?
Yeah. So I think people hope that the holographic picture works also for middle range the temperature and MC equal to 3. So in true ADS-CFT, of course, you need to go to strong coupling and also larger limit.
Yeah.
But even for QCD at lower range of temperature, we hope that it works.
Okay, thank you very much.
Thank you. So finally, using the last part of time, let me explain section 4, the reconstruction of gravity action. So this is the picture which I showed you. So in section 3 of my talk, I showed you that deep learning technique can actually gives you the concrete metric which reproduces this experimental data. So bulk reconstruction in this sense was complete. But to find out the explicit gravity model, you need to find the action whose solution is this metric. So note that in the previous section, which I used only the probe, scalar, or vector field action to have the dictionary. The metric needs to be a solution of Einstein equation. So in this section, I'll show you the reconstruction of this action. So here, I have a summary of two deep learning methods. I started with chiral condensate, and I got a part of the metric. By using hadron row meson spectrum, I can get another part of the metric. And from each of these, in fact, you can actually find a consistent dilaton gravity action with a certain dilaton potential V. Okay? If you solve this equation motion, then this metric is obtained. So in such a way, you can find this dilaton potential for this metric to be a solution of it. So this is another inverse program. And once this action is given, then you can give some other predictions, for example, about the quark mass, quark potential. So let me show you our result of the prediction and whether it matches the lattice QCD or experimental result. The result of a neural network gives us this kind of metric function. This is for H, for the case of chiral condensate. This is for the function B prime, which is the difference between dilaton and a certain part of the metric. So each of these actually can determine V of phi. So let me concentrate on the meson spectrum case. Once this is given, then you can inversely find this dilaton potential so that the equation motion of this dilaton gravity gives you this metric. And the result is this dilaton potential, where the horizontal line is the dilaton value, the vertical line is dilaton potential. This is in log scale, so you can find that this is going exponentially growing. And you can fit this function. So dots are for the numerically obtained reconstructed dilaton potential, and dashed lines are fitting. If you fit this just with hyperbolic cosine function, then you can determine this value like this. This 12 is automatically fixed by assuming that you have the asymptotically ADS spacetime. In addition to that, if you add some more power functions like this, then you can optimize this fitting by this function, where you have some values here. And it is interesting to note that, in fact, this obtained function is what Gabza and Neloa assumed in their model. So we eventually found their model by machine learning. And now, once you have the dilaton potential and the whole metric, then you can actually check for example, the exponential growth of this dilaton potential in more detail. So this exponential growth actually depends on what kind of ansatz function to fit it with. For example, let me fit this large dilaton part by this special function, exponential of some number times phi times a power of phi. So these coefficients P and Q have an important physical information. So this is the plot of the result of the fitting, where P is the horizontal line and Q is the vertical line. So these dots actually is a result of each fitting for different values of dilaton initial condition. Dilaton initial condition means that, in fact, this form is applied only for the asymptotically exponentially growing part. So depending on which part you start with, the result is different. So all of these dots are for the results of the fitting. And here you have a special value, P is 1/2 and Q is 2/3. And this cross point was expected by these authors. So they demanded that glue balls have Regge behavior. And for the glue balls to have a Regge behavior, these numbers for P and Q are determined. And it is amusing that our fitting result automatically have this point as a result of fitting. So in this way, somehow eventually we discovered the previously set up model of holographic QCD. And now about the prediction part. So what about the Koch potential computed from this model? So if you solve this action, then in string frame or Einstein frame, you can have these metric functions. And for example, in string frame, you can fit this string frame metric, the the radial component of the metric, like this, and it has a bottom here. Since it has a bottom, it produces a confining potential. And in fact, if you compute the Koch-anti-Koch potential using this gravity model, then you have this
Koji, I have some question.
Yeah, please go ahead.
Okay, so in your previous the explanation,
Yes.
As for the metric, before this one, condensation and not this one, but before you just finished.
Mm-hmm.
So the metrics, did you mention any? I haven't heard any Einstein equation you mentioned, right?
Right.
So is it automatically satisfied or
No.
no?
So
Since as a part of the deep learning, you got the metrics, right?
right.
And seems that you wrote the action naturally as a Einstein action.
Yeah.
I wonder if then the metric you got satisfies Einstein equation.
So my answer is yes or no. So in section 3, I got the metric, which is not a solution of any Einstein equation. Okay. So here, deep learning actually fixed the metric automatically just by the data, and that's it. So
right. So in that sense, doesn't have to be Einstein action. It can be something, some other action of gravity, right?
Right. So here in section 4, what I did is that I assumed that the bulk action is of the form of Einstein plus dilaton. And dilaton potential is unknown.
Mm-hmm.
Okay. And then requiring that the deep learning metric is a solution of this dilaton gravity action. What is the dilaton potential? That is a question I answered.
But as for the metric, so the potential, that's the part of the dilaton equation. It affects the dilaton equation, but still the metric should satisfy some. If you wrote that action, seems that it should be some Einstein equation.
That's right. Yeah, that's right. So from this action, you have a dilaton equation and Einstein equation, and all of those needs to be solved. And I demand that this deep learning obtained metric is a solution of all of those equations. And that determines this dilaton potential.
And that's what you impose when you solve using deep learning for the holographic ADS QCD?
No.
Oh, not at that stage. Okay.
No, yeah.
Okay. Good. Okay. Thanks.
Thank you. Maybe I can explain to you in person if you have. Yeah. Thank you.
Okay. Thanks. Okay.
So since my time is almost up, so let me finish things. So this is the Koch-anti-Koch potential computed from this model. And also from chiral condensate data, you can do the same. And then finding the dilaton potential. And for the prediction, you can compute the Wilson loop and Koch potential. And interestingly, the string breaking distance is estimated as 0.5 femtometer, which completely matches with that lattice data. So let me summarize. So I explained how a neural network can be regarded as a space-time and use that kind of identification to make the bulk reconstruction possible. So using the chiral condensate data or hadronic data from the deep learning and the assumption of the holographic QCD model, you can determine the bulk metric. And from the determined bulk metric, you can also find the dilaton potential for which it is a solution. Then from that gravity model, you can compute other quantities like Koch anti-Koch potential. And interestingly, they match lattice QCD data quite nice. Okay, thank you very much for your listening.
Speaker for a very nice talk. And does anyone have a question? Oh,
Hello.
okay.
Can I ask a question? Hello.
Yeah,
Please go ahead. Thank you.
In section 3, when you solve the equations of motion for the scalar field in the bulk, I think I'm not sure, but did you consider the back reaction, or is it not important to consider it?
No. So inclusion of back reaction means that you also need the Einstein equation, right? So
Yes.
yeah. So here I have a separation of scales. So first, for finding the metric, I just use the probe action of scalar field in the bulk. And then it determines the bulk metric. And then in section 4, I use that metric to find out the precise Einstein equation, the dilaton potential part of it. So separating the scales in this way.
Technical difficulty, I cannot hear you.
Can you hear me? Can you hear me? I cannot hear you, but do you hear me?
Yes. Yeah. I think he's gone. So.
Yeah. So I hope when he comes back, I can answer his question.
Yeah. And there is another question in.
Sorry. So I have a question about section 4.
Yeah, please go ahead.
So in section 4, if you consider a higher derivative gravity model like Gauss bonnet gravity, so will your prediction of Koch potential change, or will you obtain same prediction?
That's a good question. So I think it will change. Yes. So the point is that here I assume that the bulk gravity model is dilaton gravity. But instead of using this dilaton potential as a kind of arbitrariness of the model, you can also include higher derivative gravity model or FR gravity, for example. And requiring that this metric is a solution of FR gravity, you can actually pin down what is the function F of R, right? And in that way, gravity model can be determined from this deep learned metric function. And the prediction would be, of course, different. Yeah. So whether this dilaton gravity model or higher derivative gravity model, which one is better? It depends on the predicted result, right? And of course, you can include more fields in the bulk, but for that complicated action to be completely determined, you need more data. Yes, so if you have more data, then I think you can fix all of the function in the gravity model. And then it should be a better model. Yes.
Yeah, thank you very much.
Thank you.
Koji,
Yes, please.
I have a very naive question about the data sensitivity. That is, if you fix the gravity in the asymptotic and the horizon, right?
Mhm,
You assume horizon and you assume ADS, right?
mhm,
And then the if you assume the smoothness of the metric cannot change much
mm,
just connecting these two boundary regions, right?
right.
On the other hand, the data has a lot of, I guess, error bars.
Mhm,
So I wonder if you have very little room to vary in your metric,
mm,
and your data has such a error bars, especially
mhm.
lattice or experiment. So
Yeah.
whether you can really, I guess, vary metric in order to fit the data. So whether I mean, even in the case you arbitrarily connect these two asymptotic just by hand,
Mm,
and if you compare just those arbitrary just the connection and you calculate the result,
mm.
I'm afraid that they are not much different.
Well, yes, I agree with you. For example, for this deep learning metric, so this is asymptotic ADS part, this is a horizon part. So you connect these things like maybe straight line or just a monotonically increasing line. Yeah, it's up to you.
Right.
Yeah, but if you do that, unfortunately, this functional dependence of chiral condensate doesn't come up. It's surprisingly interesting. So what you find is that it needs to go down first and then goes up. Yeah, for this simple observation, yeah, of course, if you come up with a model which go down first and then go up, then that works well. But normally, my suspect was that it shouldn't go down since this is a metric function, and if it goes down, then it would be a very strange space-time. So I thought that it shouldn't go down, but yeah, eventually this machine found that it goes down first and then goes up, and it matches the result. So in this way, somehow this machine goes beyond our imagination and it fits the data very well. So yeah, I partly agree that there is no much room for this gravity model to reproduce detailed data. I agree with you. But interesting part is that if you loosen our kind of condition, so my imaginary conditions on this metric function, then you eventually find a nice metric.
I see. So after you found the optimized solution, so did you try to find some gravitational action whose solution has a similar behavior?
Yeah, that is what I did in section 4. Here. So from this metric, which deep learning found, I determined the gravity action, in particular this dilaton potential.
I see. So at this level, you don't need to use the, I guess, this deep learning, right?
Right. This is just solving inversely the equation of motion.
Right. Thank you for clarification.
Thank you.
A little bit related question. So your work is based on QCD data and ADS CFT dictionary. As you told you, actually the QCD is not the strictly large N gauge theory.
Right.
So do you have any estimation for the data, starting data? I mean, we have to care about the difference, the real data and actually the QCD and duality mismatches, some kind of thing.
That's a great question. Thank you very much. Yes. So for example, in this hadronic data, so I used this data of Romaison mass. So this was taken from experimental data. And experimental data has this width. However, the model of holography which I used, this is a vector field, free vector field in 5-dimensional Dilaton gravity background. If you use this model, then there is no kind of width, the decay width, since this particle doesn't decay. So once you include 1/n corrections, then it decays. So this means that the model has a limitation, and the data which I use with this width is the information of the width is not actually explicitly related to this holographic model, right? So in this way, the large n limit effect on this consideration needs a very careful treatment. So although I got a nice metric which reproduces this width too, it actually doesn't mean that it decays in this holographic model.
Okay, thank you.
Koji, I have very naive question.
Yeah, please.
So your presentation seems to be, in a sense, some inverse scattering problem, as you mentioned earlier your presentation.
Mm-hmm.
So for example, from the hadron data or chiral condensate data, you want to construct a potential, maybe also as well as metric, right?
Yes.
So if I just think about some the typical scattering data, let's say, just we are given potential, then we get all the scattering cross section. So inverse scattering problem means that from the scattering cross section, then we can reconstruct the potential, right?
Right.
In such case, I can imagine one-to-one correspondence between the potential and the scattering data. However, in this setup that you presented, unless in principle we have all the complete hadron spectrum, since you are training only based on some part of the scattering data, the hadron spectra, so in principle mathematical sense, it's not guaranteed that you get unique potential or unique metric.
Yes.
Right. In principle, there can be many possible possibilities.
Yes.
So, in that sense, what is the deep learning data you got? So you said it's optimized, right?
Yes.
Could you make some comments about this very naive question?
I think that's a very good.
Non-uniqueness, yes. So essentially, yes.
So, the metric. So let's show you this thing. So this is the metric function which we got, and as you can see, there is some width of this metric function, and this width correspond to the trials of the neural network optimization. So every time you do the optimization, you get different metrics, slightly different metrics. Since I use only 2 excitations. If I have the whole tower of excitation spectra, then I think that this is sharply obtained. But since you have only 2 things, you have some widths for obtained metric function.
Okay, I understood. Okay, thank you.
Yeah. Yeah, and there's another question in the chat. And does it have anything to do with the space-time perceived by the brain's neural network?
That's a great question. I think yes, but maybe all of you don't agree with me. Is that enough for you? Yes.
Yes, and another question, and actually I have one more last question. Actually, QC data are just numbers. So so when you get result from machine learning from QCD data. So then, sorry, I just forgot my question. Sorry. Okay, how can it tell the result? How can it tell that just result is wrong? So I mean, it might be stop some wrong position. So I mean,
Mhm.
how can we tell? How can we distinguish that?
Yes, that's a good question. So if I do training, then for example, the training actually may stop in the middle of optimization. Then we can actually compute the so-called error function. Error function
Yeah.
means that the network optimization minus the true minimum. So if this
Yes.
distance is too large, then we say that this optimization was not successful.
Yes.
So I changed the so-called hyperparameters of the neural network. So for example, the initial condition of the metric and blah,
Yeah.
blah, blah. And then I try neural network optimization again and again, then
Yes.
find out the best hyperparameters of the neural network. For example, here, in our case, the eta direction is divided by 10 dots. So
Yeah.
you can increase the number like 20 or 40. If you
Mhm.
go 50, then I found that the optimization stop in the middle. So I just need to discard that possibility.
Yeah.
So in that way, the hyperparameter was decided for the solution to be found.
Okay. I see. Thank you.
Thank you.
Is there any
Koji,
questions?
Koji, so in your answer, so I'm just wondering, how do you judge the optimization needs to stop in this case? So
Yeah,
so error function can be minimized in a way in the
that's
intermediate.
right. That's right. So so this reproduction of this figure, yeah, that's one way you can tell whether this metric is completely nice one or not. So suppose the optimization stop at somewhere, then you plot this picture by that metric, and then if it overlaps with the original data very well by seeing it, then you say that it's.
I see. So anyways, there should be some part of the I mean qualitative judgment.
That's right. That's right. Yeah, that's right.
Okay. I understand. Thank you.
Thank you.
Hello. Sorry again, but can you again repeat the back reaction thing? That time the voice got and I couldn't hear.
Thank you. Nice that you come back. So here, so I think this confused Bongfun too, but here I used two actions. The first one is a probe action in the bog, and the other is a gravity action. And the separation of these is necessary for my purpose, since this probe action was used to determine the bulk metric. And this bulk metric is used to determine the dilaton gravity action. So the separation of these two is necessary for my purpose. So if you include gravity back reaction, then these two equation motion mix with each other. And then the interpretation of neural network as a scalar field equation motion collapses.
Okay, I see. And one more follow-up question on that. While solving this, you consider the boundary values and the value at eta equals 0 as the constraint to train the neural network. But can you also put the neural network constraint such that the metric it solves also has to satisfy the Einstein's equation or something like that?
Yeah, I think it would be in principle possible, but I don't find a good way to do that. Yeah.
Okay, yeah. Thank you.
Thank you very much. If you find a way, then please let me. That's, I think, great idea.
And is there any more questions? I think if not, let's Koji for a very interesting talk.
Thank you very much. Thank you very much.
Thank you. Bye.
Bye.